We are going to start module 1 of chapter 9. In this module, we shall discuss the motion of a system of particles. In a rigid body, the distance between two particles remains same even when the body is in motion. According to this definition, it is permitted to carry on the dynamics of a system of particles. So, in this module, we shall discuss the dynamics of a system of particles. In this module, we shall discuss the equation of motion of a system of particles. Angular momentum will be defined. Euler angles will also be defined, and we shall discuss the motion of a rigid body. Now, let us find the equation of motion of a system of particles. Let a system of particles of masses small m suffix j, where j varying from 1, 2 up to n moves in space under the action of external forces given by capital F vector suffix j and internal forces. Let small f vector jk be the internal force exerted by mass mk on mass mj. Here jk are suffixes. Then f vector kj is the force exerted by mass mj on mk. By Newton's third law, we know that action and reaction are equal and opposite. This gives f vector kj equal to minus small f vector jk. Consider the figure 9.1. Let small rj vector be the position vector of mass small mj relative to the point O. O is the origin here. Let capital R vector be the position vector of the center of mass of the system. Rho vector denote the position vector of mass mj relative to an arbitrary point capital A. R vector capital AC be the position vector of C relative to capital A. Here capital AC are suffixes. Then from the definition of center of mass, we get capital R vector equal to summation over j equal to 1 to n small m suffix j into small r suffix j whole divided by capital M, where capital M is the total mass given by summation j equal to 1 to small n small m suffix j. Now, using the vector triangle law from the figure, one can find that capital R vector suffix j plus rho vector suffix j equal to small r vector suffix j. Multiplying this relation by mass small m suffix j and taking the sum over j equal to 1 to n, we get this result. After transferring the term this one on the right hand side, dividing this by capital M, we get this result. Now, we get this gives capital R vector using this result, and this and this cancels each other, so we get 0 vector. Therefore, we get an interesting result, that is summation over j equal to 1 to n small mj into row vector suffix j equal to 0 vector. If we apply Newton's second law to mass m suffix j, then we get mj into r vector suffix j equal to capital F vector suffix j plus summation over k equal to 1 to n k not equal to j small f vector jk. This is the external force and this is the internal force. For k equal to j, this will give 0, since action and reaction are equal and opposite. Summing up for j equal to 1, 2 up to n, we have this one, but we have already mentioned that this equal to 0 by Newton's third law. Therefore, we get this result. Using the formula we have already obtained, we can write this equation as this one, capital M r vector double dot equal to capital F vector, where capital F vector is the summation of j equal to 1 to n capital F j vector. Now, let us discuss about the angular momentum. Let LA vector be the angular momentum of the system of particles with respect to the point capital A. As angular momentum is the moment of linear momentum, that is angular momentum is given by this one, cross product of the linear momentum with the distance. This is the radius vector r vector suffix capital AJ, cross product m suffix j into r vector dot suffix j. This is the linear momentum. If we consider the rate of change of angular momentum, then we get LA vector dot, that is ddt of LA vector. This gives derivative of this one fixed plus this fixed and derivative of this one, which has been written here. Now, we put the value of this term and this term, also this term and this term from the figure using the vector triangle law, we get this result. Taking the product and splitting all the terms, these terms can be written explicitly here. Which can be written in this way. This gives 0 vector as the cross product of same vector vanishes. So, we get this result 0. Finally, we get this one. This one comes from this term, this term here, this term here, other terms this one vanishes, since we have already proved sum of this equal to 0, and this term also vanishes since sum of this term equal to 0. So, we get only these 3 terms. Now, let us calculate the last term here. As mass mj attracts the mass mk, similarly mass mk attracts mass mj. So, instead of fjk vector, one can replace it by fkj vector, which is the force of attraction, internal force. So, splitting this term into 2 terms here, we get this one, combining this one and this one, we get this one. Here we have used Newton's third law, which gives fkj vector equal to minus fjk vector. Since this one and this vector are parallel, so the double sum vanishes here. This vector and this vector are parallel vector. So, from the property of cross product, we get this vanishes. Thus, we have LA vector dot equal to this one plus this one. This can be combined as this one, NA vector dot, where NA vector dot is equal to summation j equal to 1 to n r vector suffix aj cross f vector j. This is the resultant moment of the external forces. Thus, we have LA vector dot equal to this one plus NA vector. This term is this one and this term is written as NA vector. NA vector is given by this. This is the resultant moment of the external forces. We now consider 2 interesting cases. Number 1, in the event the point capital A coincides with the moving center of mass C, then we have, instead of A, we have replaced A by C, then we get the result in terms of suffix C, that is LC vector dot equal to NC vector. When capital A coincides with the fixed point O, then R vector AC equal to capital R vector. Hence, the first term in the equation 9.2 vanishes, which give this one. Here, as the points A coincides with O, so the result has been written in terms of suffix O, that is the rate of change of angular momentum, this one, of the system with respect to the origin O, this comes from this point, or with respect to the moving center of mass C, this comes from this one, is equal to the resultant of the external torque about O or C respectively. This equation, equation 9.3, is called torque equation of motion. So far, we have discussed the equation of motion of a system of particles. Now, we are going to discuss the equation of motion of a rigid body. A rigid body has 6 degrees of freedom, which are the positional coordinates of its center of mass and the body set of axes of a rigid body make some angles with the fixed frame of axes, which are given by theta, phi and psi. These are Eulerian angles or Euler angles. Now, we shall define and discuss the detail about these angles. Now, we shall define Euler angles. Please go through figure 9.2. This is the line of nodes. Small ox, small oy and small oz are the body set of axes, whereas capital Ox, capital Oy, capital Oz are fixed set of axes. This is theta, this is phi, this is psi. This line is the line of nodes. This line ON is the line of nodes. Theta, phi and psi are the Euler angles. For any arbitrary motion of a rigid body, the degrees of freedom is 6, but if the rigid body rotates about a fixed point, then the degree of freedom reduces to 3. In such cases, it is convenient to use Euler angles to specify the configuration of a rigid body rotating about a fixed point. Let Ox, Oy, Oz be the space fixed axes and small ox, small oy, small oz be the body set of axes. The xy plane intersects capital XY plane along the line of nodes. Then ON is perpendicular to both small z axis and space capital Z axis. Angles between O capital N and O capital X is phi. Angle between space capital Z and body small z axis, that is between O capital Z and O small z, is theta, and angle between O capital N and O small x is psi. The motion of a rigid body can be described by means of 3 coordinates of the center of mass and the 3 angles theta, phi and psi, which determine the orientation of body set of axes O small x, O small y, O small z relative to the fixed system of axes O capital X, O capital Y, O capital Z. These angles, where phi lies between 0 and 2 pi, psi lies between 0 and 2 pi, theta lie between 0 and pi, are called Euler angles, and they represent 3 successive rotation which, when imparted to the fixed system O capital XYZ, will turn them and make them coincident with the body axis system O small xyz. Let us discuss the motion of a rigid body. In figure 9.3, a rigid body has been shown. Capital O1 is the origin, O1 capital X, O1 capital Y, O1 capital Z are the fixed set of axes, whereas O small x, O small y and O small z are body set of axes. O1 is given by capital R vector. The position vector of capital P with respect to capital O1 is RO vector. To discuss the motion of a rigid body, let the position vector of O with respect to capital O1 be capital R vector. It is considered at time t. Let theta, phi and psi be the Euler angles which determine the orientation of the body axis system with respect to the inertial system or fixed system. The position of the rigid body at time t will be determined if the 3 components of capital R vector and the 3 Euler angles theta, phi, psi are known. Thus, a rigid body is a mechanical system with 6 degrees of freedom. We take the position of the origin O at the center of mass of the body. Generally we take it. The infinitesimal displacement of a rigid body consists of two parts. First one, an infinitesimal translational displacement of the body, whereby the center of mass moves to the final position with the direction of the body axis system that remain unchanged, and this is equal to d capital R vector. Another kind of change is an infinitesimal rotation about the center of mass, whereby the remainder of the body moves to its final position, and this is equal to d phi cross R vector. Thus, we get, using vector triangle law, d small r o vector, O is in the suffix, equal to d capital R vector plus d phi cross small r vector. If we take the differential, this one, then it can be written in this way. Here we considered differential with respect to t, and this gives d dt of r o vector. This one will be d dt of capital R vector. This will be changed to d dt of phi, which can be written as omega vector. This is the angular velocity as we have given rotation. This is nothing but small v vector. This can be denoted as capital V vector suffix O. This is omega cross r. Small v vector is this one. This is the absolute velocity of the point P, whereas capital V vector suffix O given by this one is the velocity of center of mass, that is of O. This is called the translational velocity of the body. An infinitesimal rotation about the center of mass, whereby the remainder of the body moves to its final position, and this is equal to d phi cross r vector. So, from the vector triangle law, from the figure we get this result: small d r o vector equal to d capital R vector plus d phi cross small r vector. From this we get this one, this goes to this one, we get this from this one. Omega is d dt of phi, this comes from this one. If we denote this term as small v vector, this term as capital V vector suffix O, we get this result. Here small v vector is d dt of r o vector, is the absolute velocity of P, whereas capital V vector suffix O is d dt of capital R vector, which is the velocity of center of mass, that is the velocity of O. It is also known as translational velocity of the body, whereas omega is the angular velocity of the body about the instantaneous axis of rotation passing through the point O. In this module, we have discussed the equations of motion of a system of particles, and also we have defined Euler's angles. Euler's angles give the orientation of a rigid body with respect to a fixed frame or an inertial frame. In terms of Euler's angles, we have obtained the equation of motion of a rigid body.